Dr. Sucheta's interactive class. Today we'll see one of the instrument which is utilized to measure the conductance of solution, that is conductometry. In this particular video we are going to see which are the substances which can conduct electricity, the Ohm's law, specific equivalent and molar conductance, kohl-rush law, conductivity cell, its construction, measurement of cell constant, conductivity meter based on Wheatstone bridge network, and conductometric titrations. Now, if we want to classify the type of substance which can conduct electricity, we can broadly classify them as electrolytes and non-electrolytes. Electrolytes are the one which conducts electricity. There are strong electrolytes as well as weak electrolytes. Strong electrolytes dissociate easily in water to form cations and anions. These cations and anions move towards the respective electrodes, cathode and anode, and these movement of ions cause the conductivity. Whereas non-electrolytes, they do not dissociate and hence do not conduct electricity. Electrical conductance is entirely due to movement of ions. The ability of ions to transport charge depends upon mobility of ion towards the respective electrode. This mobility of ion affected by the factors such as number of ions, charge on the ions, size of the ions and temperature. As temperature increases, the dissociation. Hence, conductometric analysis is based on the measurement of electrical conductance of solution due to mobility of cations and anions towards respective electrodes. Ohm's law, which states that the current I produced due to the movement of ions is directly proportional to electromotive force and inversely proportional to resistance of a conductor, that is I equal to E upon R, where current is measured in a unit, resistance is measured in a unit ohm. Specific resistance, that is small r. The resistance of a conductor at definite temperature is directly proportional to the length of the resistance and cross-sectional area, that is capital R is directly proportional to L upon A. The proportionality constant of this equation is small r, defined as specific resistance, whereas conductance is reciprocal of resistance, C equal to 1 upon R. It is measured in the unit ohm inverse or mohos. Specific conductance, rho, it is reciprocal of specific resistance. It is reciprocal of specific resistance, that is rho equal to 1 upon R. So unit is ohm centimeter inverse. Equivalent conductance, lambda at the base V. It is the conductivity of a solution containing 1 gram equivalent of an electrolyte when it is placed between two electrodes which are 1 centimeter apart and having 1 square centimeter surface area. So lambda V equal to 1000 into rho upon C, where C is the concentration of solution in gram equivalent per liter. This equivalent conductivity increases with decrease in concentration as it is inversely proportional. Or we can measure equivalent conductance by knowing specific conductance multiplied by V, where volume is expressed in 1 gram equivalent of a solute. Molecular conductivity, mu V, it is the conductivity of a solution when 1 mole of an electrolyte is placed between two electrodes which are 1 centimeter apart and having 1 square centimeter area. Mu V equal to 1000 rho upon C, where molecular conductivity increases with decrease in concentration, where concentration is expressed in moles per liter. We can calculate molecular conductivity by knowing specific conductivity multiplied by V, where volume V is expressed in 1 gram mole of a solute. Degree of dissociation, alpha. The equivalent conductivity increases on dilution. This is due to number of ions increased on dissociation. The degree of dissociation of electrolyte is given by alpha equal to lambda V upon lambda infinity, where lambda V is the equivalent conductance at dilution V and lambda infinity equivalent conductance at infinite dilution. Hence degree of dissociation alpha can be calculated. Kohl-rush law. Now when we are calculating the equivalent conductance, if we are dissociating the ions at infinite dilution, then the ions migrate independently of its coion and contribute to the equivalent conductivity of an electrolyte. Actually, conductivity is an additive property. The number of ions all number of ions whatever are present in the solution contribute towards the conductance of solution. So, according to Kohl-rush law, at infinite dilution, ion migrates independent of its coion. So, we can contribute and say the equation regarding total equivalent conductivity of an electrolyte lambda at infinity as lambda infinity equal to lambda infinity of cations plus lambda infinity of anions. For example, in case of weak acids such as CH3COH, we can say total electrical conductivity of this particular weak acid equal to contribution of cation and anion. This increases at infinite dilution. We can measure the conductance of a solution by using a method, Wheatstone bridge method. This Wheatstone bridge instrument, it consists of, or Kohl-rush bridge we can say, it consists of a AB wire with a fixed resistance R on both ends. To increase the length of this wire, it is connected to R dash box and conductivity cell C and the headphone D, and with a small induction coil I. All of them are operated at a battery. Headphone is utilized for detection of conductance difference. This headphone is replaced by magic eye or digital device electronically. When we are interested in measure the conductance of a solution, the solution whose conductance we are interested in measuring, that is taken and placed in a conductivity cell. Here we need to maintain the temperature of the solution, so it has been kept in a thermostat to maintain the temperature of solution, as conductance depends upon temperature. The cell is connected to resistance box R on one side to a long thin wire AB stretched along a scale on other side. Now, with a known resistance R is taken out of the resistance box. An alternating current is passed through the solution with the help of induction coil. Sliding contact D is moved on the wire so that minimum or no sound is heard through the headphone. At this point, the relation of resistance of solution with respect to resistance of R equal to length BD upon length AD. This is based on Wheatstone bridge network, that knowing the value of R resistance, known resistance, length of wire AD, BD, we can calculate conductivity of solution by taking reciprocal of resistance of solution. This is the conductometer instrument nowadays we are using in a lab, where on this digital device we'll get directly the conductance by dipping this conductivity cell in a salt solution. We can maintain the temperature constant over here and find out the conductance of given solution. The conductivity cells which are utilized in these conductometers, these are made up of highly insoluble glass such as Gina, Pyrex or quartz. It consists of a pair of platinum electrodes which are coated with platinum black, hence named as platinized platinum black. This coating minimizes the polarization effect, and conductance is measured just by dipping this cell inside the solution. There are different types of cells available in the market. Among them, we are utilizing the type B. In this type, you just need to dip the cell inside the solution to measure the conductance. Type A, where the electrodes are far apart from each other to measure the higher conductance, whereas type C, the large electrodes are placed with a small distance, and this type of cell is mainly used for low conductance measurement. To perform the work accurately, we need to prepare the solutions of solute in pure water so that we can minimize the conductance obtained due to the solvent or due to impurities. For that purpose, we need to utilize conductivity water. We can prepare the conductivity water by taking distilled water or distilling the water with KMnO4 or KOH in distillation unit and carry out that distillation process. Obtained water, we can call it as an conductivity water. We can place or preserve that water in a glass flask for a longer time to do the experimental work by utilizing this conductivity water. Pure water exhibits low conductivity. Water having conductivity 3 into 10 to the power minus 7 moles can be utilized, or absolutely pure water can be utilized as a conductivity water. Once we prepare the solution, before measurement of actual conductance, we need to determine the cell constant of a conductivity cell. That is actually a calibration step of conductometer. Once we perform this step and we know the cell constant expected to be 1, then we can move forward for measurement of conductance. The electrodes in a cell are not exactly 1 centimeter apart, which is expected, or may not have a surface area of 1 square centimeter. So we need to find out cell constant. Thus, the value of observed conductivity is not exactly equal to specific conductivity but proportional to it. So we can find out cell constant by, when multiplied by observed conductivity gives the value of specific conductivity. It is already mentioned that R resistance equal to rho into L upon A, where rho into L upon A. L upon A is the cell constant. Length 1 centimeter and A 1 square centimeter. So this cell constant is always expected to be 1. Another way to find out this value is by utilizing this equation by R and rho, or cell constant. If you rearrange the equation, we will get R upon rho, or cell constant equal to 1 upon observed conductivity divided by 1 upon specific conductivity, or specific conductivity equal to cell constant into observed conductivity. Specific conductivity at 25 degrees Celsius solution for this electrolyte like KCl. It is strong electrolyte, dissociates completely. So as a standard solution, we always prefer and utilizing this solution 1 upon 50 N by 50 solution. We are utilizing it 0.05 normal solution of KCl, and this known specific conductivity, if we'll place in the value over here and find out the observed conductivity of the same solution, we can find out cell constant. So specific conductivity value is provided to you. Observed conductivity of same KCl solution you need to find out by utilizing your instrument to know the cell constant. The factors affecting conductance. As temperature increases, mobility of ion increases. So temperature, maintaining the temperature is one of the important factor to find out the exact conductance. Concentration of solution. If we take too high concentration, number of ions are very high, then mobility will decrease and hence conductivity decreases. So dilute solutions are usually preferred to measure the conductance. Number of ions present in the solution cause directly proportional to the conductance of solution, and size of ions. It is inversely proportional. Conductivity is inversely proportional to the size of ions. Smaller the size, it can move fast. By utilizing this conductometer, we can measure the conductance. We can perform conductometric titrations by utilizing conductivity meter by dipping this cell in a, here we are not taking conical flask, we are taking beaker to carry out the titration, where you need to put conductivity meter where conductivity cell is placed, attach this, fix the position of conductivity cell. Never ever utilize conductivity cell to stir the solution. Burette, you have to add this in such a way. Microburette are preferred over here. Small amount of addition of your titrant towards your analyte. For every addition of this titrant towards your analyte, and after utilizing this magnetic stirrer which will stir the solution, make it of the magnetic stirrer, wait for some time and find out the conductance of your titration. As the ions are moving, you may get the last digit as uncertain. You wait for some time and write down the reading during conductometric measurements. We can classify the number of titration which can be performed by conductometric titration as acid-base titration. We are going to see 4 different types of acid-base titration: complexometric titration, precipitation titration and redox titration. We'll start with acid-base titration. Simple example, we have taken over here strong acid, strong base. Strong acid, you all know, HCl, strong base, NaOH. We are performing this titration. We have performed this titration. You might have performed this titration with use of indicator. So without using indicator, you are performing the titration over here. So your solution is colorless throughout. So end point is measured by measuring the conductivity throughout the titration. You have to fill the solution burette with HCl, NaOH, and HCl is there in a beaker. Now when initially you are measuring the conductance of solution which is there in the beaker. So for HCl it is high conductivity. As you are putting NaOH, formation of salt and water decreases the conductivity. After equivalence point, excess of addition of NaOH towards your beaker or analyte titrating flask increases the conductivity of a solution. So extrapolating these two straight lines on a graph, you can get the equivalence point or end point of your titration. Second example, strong acid, weak base, HCl versus NH4OH. We are putting base in the burette and HCl in the beaker. Initially again here also conductivity is higher because of H plus ion. As the formation of salt and water takes place, conductivity decreases. Now this is weak acid, so it will dissociate slow or weakly. So conductance will decrease or remains constant in this case, and you are getting a plateau after equivalence point. You can write down the reactions. HCl plus NH4OH equal to salt and water. Weak acid, strong base. Weak acid CH3COH and strong base NaOH. Weak acid we have taken in a beaker. We have started the titration by addition of NaOH. Initially weak acid dissociates and produce low the H plus ion, so increase in conductivity till you will form the CH3COH plus NaOH. You will form CH3CONa plus water. When the salt formation complete, excess of addition of NaOH towards your solution increases gradually the conductivity, and you will get increase in conductivity for OH minus ions. Weak acid, weak base titration usually not possible without indicator routinely in a lab. So this particular instrument will give you equivalence point for weak acid, weak base titration like CH3COH and NH4OH. Weak acid dissociates slowly and combines with NH4OH to form a salt CH3COO NH4 and water. So increase in conductivity during salt formation, and you will see over here as both are weak acid, weak base, the conductivity measurements are very slow or very gradual increase you have observed over here, and then the plateau is observed for excess of addition of NH4OH. Redox titration. We are learning over here redox titration of ferrous ion with dichromate. Redox ion increase in oxidation number. Fe2 plus has been converted into Fe3 plus and Cr2 plus. Dichromate we are utilizing in presence of HCl. In this particular method, as initially you are having H plus ion which is having high conductivity, as the reaction takes place and convert Fe3 plus, utilization of H plus ion to form water, hence decrease in conductivity is observed till complete oxidation of particular Fe3 plus is observed, and after After equivalence point, excess of addition of dichromate ion towards Fe plus ion shows constant or plateau for conductivity measurement. Complexometric titration. We are taking here an example of complexometric titration which was first proposed by Werner. In this method, two endpoints are observed. First is formation of metal ion and second is for formation of complex. We'll see how this happens. Titration of potassium chloride with mercury chlorate. Initially, potassium chloride reacts with mercury chlorate to form mercury chloride and potassium ion. Once this particular step is complete, then for excess of addition of KCl solution, mix mercury chloride converted into potassium mercury chlorate, and this is the second endpoint obtained during the titration. So you need to extrapolate these lines to find out two equivalence points formed during the titration, first for metal ion and second for complex formation. Precipitation titration. Precipitation titration, here we are taking a simple example of silver nitrate versus KCl solution. Silver nitrate is there in a beaker and KCl as a titrant you are utilizing. Usually, to detect the end point of precipitation titration is not easy task by routine precipitation titration. So, when we are adding KCl solution to AgNO3, formation of precipitate decreases the conductivity or remains constant, so initially plateau is observed. Once the complete precipitation and formation of AgCl is over, excess of addition of KCl increases the conductivity and a deep rise is observed in a graph. Extrapolation of these two lines will give you endpoint during the titration. This is a second example of precipitation titration where two different precipitates are obtained during the titration. It is a titration between magnesium sulfate with barium hydroxide. Magnesium sulfate form magnesium hydroxide and barium hydroxide form barium sulfate. So initially magnesium hydroxide converted into magnesium hydroxide formation takes place as you are adding barium hydroxide into the solution of MgSO4. So decrease in conductivity is observed during formation of magnesium hydroxide. Once the magnesium hydroxide formation is completed, excess of addition of barium hydroxide towards the solution shows increase in conductivity during the formation of barium sulfate. So looking at these broad applications of conductometric titrations, we can quote definitely the different advantages over here as no need of indicator, suitable for colored solution, accurate results are obtained with regard to endpoint by utilizing graph, analysis using turbid solution, weak acid, weak bases, mixture of weak acid and strong acid is possible. Just need to maintain the temperature constant and we can utilize this for dilute solution. The disadvantage we can quote under this heading is increased level of salt solution can mask the conductivity changes and which will not give the accurate results. Application of conductometric titration to redox system is limited because high concentration of hydronium ion in solution tend to mask the change in conductance. Applications. I can apply this conductometer measurement, conductometric titration I can carry out for determination of basicity of acid. Basicity defines over here as number of carboxylic acid groups attached to the molecule. Determination of conductivity of sparingly soluble salts such as barium sulfate, lead sulfate. We can measure here the conductivity of these solutions at room temperature and conductivity at temperature higher than the room temperature, how it differs with the dissociation of ions. Determination of purity of water, as for pure water you know the conductivity. So if the water is impure, definitely the conductivity will rise due to presence of impurity in the form of salt. Determination of salinity of the seawater. Increase in the salt content increases the conductivity. You can apply the same information over here to determine the salinity of seawater. Determination of ionic product of water. Quantitative analysis of compounds. There is broad application of this particular instrument. You can determine the sulfur oxide in air pollution studies, determination of soap in oil, accelerators in rubber, total soap in latex, specific conductance of water, alkalinity of fresh water, deuterium ion concentration, and trace the microorganism, tracing the antibiotics. So these are the broad application area with respect to conductometer. These are the few references I have quoted over here for you to explore more information about this conductometry. Hope you have understood today the conductometer, its basic law, applications, conductivity cell. Thank you. Hope you like this video. Please share.